Hello everyone, welcome to lecture number 26 of this NPTEL course on Riemannian geometry. So as I was saying at the end of the previous lecture that in the next couple of lectures we are going to talk about the geometry of submanifolds, and we learn how to let us say you have an embedded surface inside R3 with the induced Riemannian metric. We learn how to calculate the curvature of such manifolds. Okay, so here is the setting. Okay, so let Mg be a Riemannian submanifold of some Riemannian manifold M tilde G tilde. So let this be a Riemannian hypersurface So why do I call it a hypersurface? That just means that the dimension of the ambient manifold, so this M tilde is called the ambient manifold. The dimension of this is the dimension of M plus 1, or equivalently we say that the codimension of M is 1. Okay. So the entire discussion that we are going to have today has an analog even for higher codimensional submanifolds, but since most of the examples that we are interested in will arise as hypersurfaces inside the Euclidean space, for instance like the sphere, I thought for simplicity one could just restrict our attention to hypersurfaces for these lectures. So then I am going to denote the Levi-Civita connections by nabla and nabla tilde. So let these be the Levi-Civita connections respectively. Okay. So the first point of observation is that at each P I have an orthogonal decomposition of the tangent space. So if you look at the tangent space to M tilde, then that decomposes as the tangent space of M plus an orthogonal direction which I will denote by NPM. Okay. So NPM is simply the orthogonal complement of the tangent space. Okay. So by definition this is basically the set of all vectors V in the tangent space of the ambient manifold which are orthogonal to all vectors which are tangential to your submanifold M. Okay, so let me just draw maybe a picture. For simplicity, let us just take M tilde G tilde to be the Euclidean space, because these are essentially where all our examples are going to come from, and let us take a surface, right. So this is your M with the induced metric G. Okay, so if you are at a point P, you have the tangent space to your M at, sorry, let me maybe draw it slightly better. Okay, so suppose you have your point P here, you have the tangent space, and then you have the orthogonal direction which is basically NPM, right. And so note that the dimension, because we are working with hypersurfaces, the dimension of this is just 1. And we will denote by the corresponding bundle, we will denote or the corresponding disjoint union over all points P, we will denote that by Nm. So now you have natural projection maps we have the tangential projection at each point P, we have the tangential projection from this to TPM, and we have the orthogonal projection from TPM tilde to NPM. Okay, right. So the key definition is that of a unit normal field. So before that, I define what I mean by a smooth normal field. A smooth normal field to M is basically a map. I will usually denote normal vectors by nu or by capital N. So this is a map from M to the space of the normal vectors Nm such that the following conditions hold. Firstly, for all points P in M, nu P should be a normal vector at P. So nu P should lie in NP of M, this one dimensional vector space. Secondly, I want nu to be smooth. What do I mean by that? So if you know a little bit about vector bundles, then this Nm basically forms a rank 1 vector bundle, and then you just want nu to be a smooth section. If you do not know about vector bundles, let me just define for you what smoothness means in this context. So in the sense that if x1 to xn plus 1 are local coordinates on some open set u tilde in M tilde, such that M intersected with u tilde is basically given by a slice where the n plus first component is 0. One can always choose such coordinates so that M is given by this slice where the n plus first component is 0. So then I want my normal field restricted to M intersected with u tilde at a point x to be of the form summation I going from 1 to n plus 1 nu I of the components depend only on the first n coordinates, because the first n coordinates are basically give you coordinates on M intersected with u tilde times del by del xi, okay, where each of these nu i's is a smooth function on this intersection. So it is a smooth function in the first n coordinates, okay, and then I will denote by n of M. This is the space of all normal fields. Okay. So my standing assumption that I will make throughout these two lectures on the geometry of submanifolds is that M is two-sided in M tilde, which basically means the following, that is, there exists a normal field such that the norm of this normal field is identically 1. So M being two-sided, at least for me, by definition just means that there exists a unit normal vector field along M. So of course an equivalent definition is that there is a normal vector field that never vanishes, so then you could just normalize by the norm of that vector field at each point to get a unit normal vector field, right. Okay. So for example, I do not want things like the Mobius strip in R3, right. So I want M to be two-sided. That's going to be my assumption throughout. I'm not going to repeat this. Okay, so an example of this is a typical example that will be of main interest to us will be the following. So let f be a smooth function on Rn plus 1 on some open set in Rn plus 1. Okay, and C is a regular value. Then we take M to be the level set of C. So the inverse image of C under F. Then by the implicit function theorem, this is a smooth manifold and smooth embedded manifold inside Rn plus 1, and you take G to be simply the restriction of the Euclidean metric to M, right. And then clearly this is two-sided because I can take the unit normal vector to simply be the gradient vector field normalized to have norm 1, okay. So the fact that the gradient vector field does not vanish is equivalent to the statement that C is a regular value, right. So this is a typical example of a two-sided surface that we will be interested in. Alright, so some additional notation. So I will denote by chi m tilde restricted to M to be the vector fields of M tilde restricted to M. Okay. So this is basically the vector fields which take values in the tangent bundle of M tilde, but they are defined potentially only on M. So just to draw a picture again. So at each point you basically have a vector field that takes values. So at each p your xp will take values in the tangent space of the ambient manifold, but this is potentially only defined over M, okay. So of course something like Whitney's extension theorem or using partitions of unity, given any such vector field I can always extend it to a vector field on the entire M tilde, but when I am looking at this space I really do not care so much about its values outside of this embedded submanifold M. So the key proposition is the following: there exists a unique map which I will denote by nabla tilde. Remember, nabla tilde was the connection on M tilde. I will denote this map by nabla tilde with a superscript of M. So this takes in vector fields on M and spits out a vector field in this space, okay, satisfying the usual properties that a connection is expected to satisfy. So let me write down. So if for all f1 f2 in C infinity of M and for all x1 x2 y in chi of M, we want it to be C infinity linear in the first variable. So this is equal to f1 okay, The second property is some sort of a Leibniz rule. I want this to be equal to x of f times y plus f times this, and the third property is the key defining property. So, whenever you have vector fields of the ambient manifold and you take restrictions to M such that x and y give you vector fields on M, then in fact if you compute this, this will simply be the Levi-Civita connection of the ambient manifold applied to x tilde y tilde, and you restrict this to M. Okay. So, here the key assumption is that the restriction of these vector fields to M actually takes values in the tangent space of M rather than the tangent space of M tilde, so that this object is well defined, right, because if you go to the previous slide, this was defined on a product of the tangent spaces of M, right. So, I need this key extension property. So, the proof I am not going to go over the details, sorry, let me this is not the complete proposition. So, moreover I have the following properties. So, the first three properties are enough to define a unique operator, but then we will have the additional following properties, that if you take the Levi-Civita connection, the covariant derivative of y in the direction of x, then that is simply given obtained by applying this new operator to these. Now, this will give you a vector field of M tilde restricted to M. So, in order to get something that is a vector field on M, you basically take the tangential projection. Okay, so this is the tangential projection. Okay. And fifth, this new operator will also satisfy torsion freeness in a certain way. So, this is equal to x y. Okay. So, I am not going to prove the proposition, this is a good exercise. Let me just tell you that this is similar to when we define covariant derivatives along curves, and this basically relies on the this locality property. So, so a hint for this exercise is one uses 3 as a definition. Okay, so in other words, let me just explain what I mean and then I will leave the details as an exercise. So, given two vector fields on M, let x tilde y tilde be arbitrary extensions using, say, partitions of unity or something. So, just to give you an example, you have a vector field that is sort of tangential along this manifold, then you just sort of extend this arbitrarily to a vector field on the entire ambient manifold, and you simply define this. Now this is a definition, is simply the covariant derivative of y tilde in the direction with respect to x tilde in the ambient space, okay, and restrict all of this to M. And the key claim that you need to show is that that definition is independent of the extension. So as long as x tilde and y tilde satisfy the property that restricted to M, they are basically equal to x and y. It does not matter what extension you pick, you will always get the same definition, and this is because of our locality theorems, okay. This, if you remember, this is the exact same thing that we did also for when we wanted to define covariant derivatives along curves. Right. So, this is exactly, I mean, curve is basically just like a one dimensional submanifold, right. So, this is exactly the same sort of thing that we had done. Okay, so I will leave the details as an exercise for you guys to work out. So, now I come to the main sort of central definition in this whole subject, namely the second fundamental form. The second fundamental form is defined by so it is a map that takes in two vector fields of M and spits out a real number. So, h of x comma y is simply the normal component of this. So, you take this operator, newly defined operator, you take the normal the component along this unit normal vector, okay. So, then a lemma that one needs to show is that H is in fact a 0 to tensor on M and is symmetric. Okay. So, again I will leave the proof as an exercise. So, these are actually, I mean, if you really want to learn the subject, these are exercises that you must try by yourself, because I mean that is, I think, the only way to learn the subject, to actually get your hands dirty and really do these exercises for yourself. Okay. So, let me again give you maybe a hint that the symmetry follows from basically property 5 above, okay. All right. So, so now the key proposition that I want to prove is the following. So, the first part is the so called Gauss equation, which says that if you take this operator applied to y with respect to x, then that is simply the intrinsic Levi-Civita covariant derivative of y with respect to x plus a term, correction term given by precisely the second fundamental form. As you will see, this is essentially from the definition of the second fundamental form. Then we have the following useful theorem by Weingarten, that there is a formula for the second fundamental form. This is precisely minus the inner product of the normal of the derivative of the normal vector with respect to x comma y. Okay, and then third, the key equation called the Gauss-Codazzi equation, which helps us compute the curvature tensor. So, for all x, y, z, w, which are so let me maybe localize at a point. So, which are or sorry, let me yeah. So, if you take the curvature tensor of M, that is the curvature tensor of M tilde plus the correction term that comes from the second fundamental form. So, plus HP of XP WP, HP of YP ZP minus HP of XP ZP, HP of YP WP. Okay. So, let me now prove this proposition. Okay, so the Gauss equation, as I said, is from definition, because we have already observed that if you take the intrinsic covariant derivative of y with respect to x, then that is simply the tangential component of this. On the other hand, what is h x y? By definition, that is simply the normal component, right. So, this times nu hat is simply the normal component, and so when you add these up, you get the entire nabla tilde of y with respect to x. Okay, so that proves the first part. For the second part, we note that because nu hat is normal and y is tangential to M, their inner product is always 0. So, if you differentiate this inner product in the direction of x, that is also going to be 0, but by the fact that these are metric connections, this is simply in the statement this should not be M, because nu hat is not a vector field on M, it is a vector field, it is one of these restricted vector fields, right. Plus, so by the product rule for metric connections, this is just this. Okay, but the second term by definition is precisely the second fundamental form. So, that means that if you take this, okay. So, the moral of this story is that the second fundamental form captures the derivative in some sense of the unit normal vector. Okay, so how the unit normal vector twists and turns, that is what is captured by essentially the second fundamental form. Okay. So, if you remember in the first lecture, I as a motivation for curvature of surfaces in R3, I had said that one way to think about curvature, a surface is really curved if the normal vector, the rate of change of the unit normal vector is really large, right. So, then it is not surprising that the formula, the Gauss-Codazzi equation basically relates the curvature of M to the curvature of the ambient manifold and the second fundamental form, which captures how your normal vector is sort of changing. Okay, so, now let us prove the Gauss-Codazzi equation. So, because this happens at a point we can always work, so it is enough to prove this for coordinate vector fields, i.e. I can always assume that x is given by del I, y is given by some del j, z is given by some del k, and w is given by some del l, right, because every other vector is a linear combination of these, and then I could just use multilinearity. Both the RHS and LHS have this multilinearity, so it's enough to prove this identity for these basis vectors. The advantage of these is that I have the following commutation formulae, right, etc. Okay, so that makes the calculations much easier. Okay, so let's now compute. So let's take Rm tilde of this. So by definition also, because these sort of vector fields commute, this is the same as this, right. Okay, so let's compute the first term. So I use the Gauss equation to write this as the intrinsic derivative of del k with respect to del j, and then there will be a second fundamental form term. So plus del I h of del j del k times the unit normal vector times del k. Okay. So I keep the first term as it is. For the second term I use product rule. So the first thing will be when this del I term hits this, so you will have del I of the second fundamental form times this, plus you will have the second fundamental form term times this. Okay. Now this term is going to be 0. Why? Because nu hat and del L are orthogonal to each other. Okay. So also in the first term I again use Gauss equation. Okay, so if I again use Gauss equation, I will again get two terms. One will be the intrinsic nabla del I del j del k acting on inner product with del L, plus again there will be a second fundamental form term h of del I comma this times nu hat times del L okay, plus this final term which is this, but by the Weingarten equation this is also equal to minus h of del I del L, right. So I just replace this plus sign with a minus H of del I comma del L. Okay. Also once again, because nu hat is normal to the surface, this is going to be 0. Okay. So the second term is going to be 0. So you end up finally with the following formula, that you started off with this, that is equal to the intrinsic derivatives minus H of del I del L times H of del J del K. Okay. Similarly, now interchanging the role of I and J, you get this just by symmetry, right. Del J del L H of del I del K. Now just subtract the two. So on the right you will get Rm tilde acting on this. On the left, the first two terms, if you subtract, you will get Rm of this, and then you basically get minus this. Okay, so if you take the second fundamental form terms to the other side, you get precisely the formula in the Gauss-Codazzi equation. Alright, so this proves the Gauss-Codazzi equation. So I will end with the following remark. Note that H depends on the choice of nu hat. So at any point there is basically just two choices of the unit normal vector field, because it is one dimensional. So you could have either picked nu hat or you could have picked minus nu hat. H clearly depends on your choice, but the curvature does not, and it should not, right, because the curvature is an intrinsic property of the embedded submanifold. Why does it not depend on the choice? Because if you make the choice of minus nu hat, the second fundamental form will change to minus H, but Rm involves minus H multiplied by minus H, which is just H multiplied by H, right, terms of the form H multiplied by H. So that sign is independent of the choice of the unit normal vector field, which again, as I said, makes sense because the curvature is an intrinsic property of the embedded Riemannian submanifold, whereas the second fundamental form is an extrinsic property, so it depends also on the choice of this unit normal vector. Alright, so that is it for this lecture. In the next lecture I will continue this discussion and actually use the Gauss-Codazzi equation to calculate some curvatures, and we will also introduce this thing called as the shape operator, which makes these calculations much more streamlined. Okay, so that is the content of the next lecture. Thank you for your attention, and I will see you next time. Thanks.